Hello and welcome to follow my video course Introduction to Flow Mechanics. My name is Matti Ylitalo and I'm your teacher during this course. In this video our topic is natural convection. What natural convection means and how it develops. That's the topic in our video. Natural convection, which is often called free convection, is heat transfer and fluid motion which develops without any external force like pumps and fans. Here we have a couple of examples. In this first one we have a room and there is a radiator, and when we have this radiator it means that we warm up our air and it becomes less dense, so it's rising up, and it means that it's pushing colder air downwards, so we will have this kind of circulation flow in our room. Another example is this kind of teapot on a stove. Here we have hot water near the bottom of this pot, and it's rising upwards and it creates this circulation flow when we have colder water coming downwards. Let's take an example and calculate the maximum velocity above the radiator. When we have this kind of vertical flat plate, we will have boundary layer development which starts from the bottom of the plate, and the velocity profile will be something like this. Because our plate is not moving, so the velocity at the surface of the plate must be zero. And now when our plate temperature is higher than the temperature of the environment, our temperature profile will be something like this. When you need to calculate the maximum velocity about this kind of radiator, you can use this kind of function. Here we have the temperature difference, which is the temperature difference between the surface and environment. And then you have this kind of thermal expansion coefficient, and for that you can use a function 1 divided by so-called film temperature, and for this film temperature you can use the average value of the temperature of that plate and environment. For this L you can use the height of the radiator. Please note that this maximum velocity function is an approximation. If you want to take into account all geometry details in that radiator geometry, you need to use CFD tools. I asked ChatGPT to give a Python code, and using this Python code I calculated an example case. We have a surface temperature 70 degrees C and the room temperature 22 degrees C, and from these results we see that the maximum velocity above the radiator is 0.9 meters per second. So we are talking about very low velocities. Why this temperature difference creates fluid motion? From basic physics we know that when air is heated, the air molecules gain energy and they spread apart. And this means that the hot air becomes less dense. And we can calculate that density from this function. We have here this thermal expansion coefficient and this temperature difference. In this curve we can see how air density is changing when the temperature is increasing. When we have temperature differences, we have these density differences, and it means that we have so-called buoyance force. Buoyance force is upward force, and it's proportional to these density differences. Here is an example. We have a hot air balloon, and we are warming up the air inside this balloon, so we will have a density difference between our balloon and environment, and it means that we have this buoyance force upwards and we can fly. Let's take an example and calculate the heat transfer from a radiator to room. In this kind of case we need to take into account both convection and thermal radiation. Here is seen how we can calculate the heat transfer from our vertical plate. And first we need to define this so-called film temperature, which is the average of our surface temperature and room temperature. Then we need this thermal expansion coefficient, and we can use function 1 divided by this film temperature. Then we need Grashof number, which is the function of this temperature difference and height of our plate. And then we need this Rayleigh number, which is Grashof number times Prandtl number. And finally, using this Rayleigh number, we can calculate this Nusselt number, and the Nusselt number is giving us this heat transfer coefficient. The K here is the thermal conductivity of air, and L is the height of our plate. To take into account radiation, we can use this function. We have here the surface temperature to the fourth power, and we have this environment, this room temperature to the fourth power. And for surface emissivity, we can use, for example, 0.8. I asked this Python code from ChatGPT, and using this code I calculated an example case, and we have here the plate temperature 70 degrees C and room temperature 22 degrees C. And the height of our radiator is 0.6 meter, and the width is 0.5 meter. And from these results we can see that this convective heat transfer was almost 56 watts, but the radiation was 96.1 watts. So the radiation was even higher than the convection in this case. If you are interested on boundary layer thicknesses, you can use this function. This is for velocity boundary layer thickness, and this one for thermal boundary layer thickness. And I calculated the thicknesses of boundary layers to our previous example, and the velocity boundary layer thickness was 14 millimeter, and the thermal boundary layer thickness 15 millimeter. Here is an example of a more challenging case. We have a horizontal flat plate which is heated to 70 degrees C, and our environment is at 20 degrees C. And we want to know the heat flux from this plate to environment. I calculated this case in ChatGPT, and here are the assumptions which were used. Those material properties were taken at average temperature, in this case 45 degrees C, and here are those key non-dimensional numbers. This thermal expansion coefficient, the temperature difference was 50 degrees C, and using these values we got this Rayleigh number which is shown here. And now this Rayleigh number is at level so that this case is not laminar anymore, but it's not fully turbulent. So we are in a transition zone, and it means that to calculate the heat transfer we are now in a very challenging case. Here we have two correlations with which we can calculate the heat flux from this horizontal plate. This first one is shown here. We have a correlation for Nusselt number from which we can calculate this heat transfer coefficient, and when we know the temperature difference and we know the surface area, we can calculate the heat flux. It's now 209 watts. And there is another correlation to calculate this Nusselt number. This is made for more turbulent flow case, and from that we can calculate this heat transfer coefficient, and finally this heat flux. It's now 305 watts. So there is quite big difference between these two values, and we can conclude that in this kind of case, when we are in this transition situation, we can give only a rough estimate to heat flux. Here is an example of natural convection in a vertical slot. In this picture on the right side we can see our plates. This left one is heated and this right one is insulated, and there is a gap S between those plates. And now we can separate two different situations depending on this distance S. If this distance is so big that when our boundary layer develops, it behaves like in an isolated vertical plate case, then we can use these correlations to calculate this Nusselt number and heat transfer, and use in those functions this characteristic length, the height of this plate. But the other case is that if this gap is so small that our boundary layer will fill this gap totally, then we can calculate this case so that we use characteristic length S, which is the distance between these plates. Here is some kind of guideline how we can solve this kind of problem. First we need to calculate our film temperature, and then we need to check the boundary layer thickness, so that we can say is our case so-called isolated vertical plate case or is it a so-called confined case? And then we can pick the right correlations and calculate this Nusselt number, and from that this heat transfer coefficient and then this heat flux. I calculated an example case using Python code, and in this case this distance is 0.1 meter and the height of the plates is 2 meters and the temperature of the heated plate was 70 degrees C and the temperature of the other plate 20 degrees C, and here we see the results. This is showing the normalized velocity profile and this red one normalized temperature profile near the top of the slot. And in this case we have so-called isolated vertical plate. Here we have a fin heat transfer example. This is the same case as was calculated earlier in a simulating fin heat transfer video. The basic question is that we have a ship and we are asking which is the maximum power of this ship when we want that the maximum temperature is below 85 degrees C. Here you can see the detailed description of this problem. I asked a Python code from ChatGPT, and using that code I calculated this natural convection case, and the results are shown here. So depending on this cooling air inlet temperature, the maximum power of the ship is at level of 5 to 11 watts. And on the right side you see the result for this forced convection case. Then this maximum power was at the level of 22 to 42 watts. So the maximum power is much less if we have this only natural convection. Okay, that was all this time. Thank you for watching and see you. Bye bye.